Imagine an endless, blank, two-dimensional plane stretching out in all directions. Now, drop a single geometric point into that empty void. In this raw environment, there is no objective way to define the point's exact location. Without a reference framework, we are forced to use relative descriptions, saying the point is somewhere in the top right. In fields like surveying or structural design, this lack of specificity makes it impossible to replicate the point's position for other people or machines. To calculate space with accuracy, we need a standard system that converts these visual positions into numerical data. We begin to constrain the space by placing a horizontal axis beneath the point, establishing a real number system. This creates a one-dimensional range. By dropping a line to the axis, we describe the point's horizontal position as a value between 0 and 5. However, this system remains incomplete. It tells us the point's location along the line, but it cannot measure how far the point sits above it. To fully lock the precise position in two-dimensional space, we must introduce a second, completely vertical, intersecting axis to the system. We introduce a vertical number line that bisects the horizontal line at its 0 mark. The point where these two lines meet serves as the fixed reference for the entire plane. This is the origin. This system relies on orthogonality, the requirement that the two axes intersect at a 90-degree angle. This right-angled construction is why this is formally known as a rectangular coordinate system. By convention, we label the horizontal axis as x and the vertical axis as y. Every location in the plane can now be expressed as an ordered pair, a set of coordinates written as x, y. Because the axes are perpendicular, the horizontal and vertical values remain independent. Changing one coordinate does not alter the other. To find the point 3, 4, we start at the origin and travel 3 units along the x-axis. From that position, we travel 4 units vertically to reach our destination. The system works identically for negative values, using -5, 2 as an example. We move 5 units left of the origin on the x-axis. We then move 2 units up the positive side of the y-axis to finalize the location. This address system provides a unique and unambiguous identity for any point in the plane. When these axes intersect, they divide the coordinate plane into 4 parts. These sections are called quadrants, labeled 1 through 4 in a counterclockwise direction. Each quadrant is defined by its parity, the specific combination of positive and negative signs in its coordinates. In quadrant 1, both the x and y coordinates are always positive. In quadrant 3, both coordinates are always negative. Quadrants 2 and 4 have mixed parity, where one coordinate is positive and the other is negative. Understanding these parity rules allow us to categorize data points based on their signs before we even plot them on a grid. If every point belongs to a quadrant based on its signs, where do we place coordinates like 5, 0? Because one value is 0, this point does not lie in any quadrant. It sits directly on the x-axis. Points with a 0 value exist only on the boundary lines. These boundary points define the edges that separate the 4 quadrants from one another. This partitioning of space has practical benefits when graphing real-world data. Many datasets, such as time or height, do not use negative numbers. In these cases, we can ignore the other 3 quadrants and focus our entire grid on quadrant 1. By scaling the grid to fit only the relevant data, we can see smaller details and more precise changes within the same viewing area. By combining a fixed origin with perpendicular axes, we have created a matrix that links geometry to numbers. This structure replaces vague spatial descriptions with constant numerical values. Once a point is expressed as a set of numbers, it can be processed by a computer. This is how complex physical shapes are stored as data, by breaking them down into a series of coordinates. This conversion of visual space into computable logic is what allows us to model physical objects and navigate digital maps with consistent accuracy.